I think we've got that going, so I've just got to monitor that at 45 minutes. I say that every week and then I go over. Alright, so for the know-how part of the evening, it's kind of a bit of a bridge between what you do normally anyway and something that's relatively new. Now, I suspect that you would have been taught this to some degree in maths. I didn't do any matrices with you, did I? In Calculus 2, so it was Calculus 1 that you did it. I don't think we did any, did we? I can't recall. Okay, so what we've got here is a couple of lines, and we'll just call this one y equals x, so y equals x plus 2, and this one down here is y equals negative x plus 4, and so we've got this point where they're coincident, and you'd be teaching this at school anyway at some point, and y equals y, which is pointless. But what we notice is that's the left hand side of the equation. The right hand side of the equation is saying that minus x plus 4 is equal to x plus 2 at some point, and that's where the x's coincide for the solution. So I'll add the x's. You've probably done this a million times with quadratics and God knows what else, and that's fine. So we've got 4 equals 2x plus 2. So I can subtract the 2 from both sides. So I get 2 equals 2x. Divide the 2 both sides, and I get x is equal to 1. So that point there is x equals 1. Alright, so that's kind of the secondary school way of dealing with the two equations with two unknowns. Now, I think I did do this with you early on, did I? Did I do this? No, I don't think I did in ours. You may have seen it in the Maths 1 one. Alright, so the way that we would write this up, we would write it as y is equal to x plus 2 and y is equal to minus x plus 4, and then what we'll do is we'll put the x's over the other side. So I'm going to subtract x so it goes on that side. So I've got, and I'm going to put it on the inside of the y. So I'm going to do y minus x. Now I'm spacing them deliberately, 2, and I'm going to put the x on the other side by plussing it. Y plus x is equal to 4. Okay, so what we've got there is now we're going to augment this. So we've got 1 minus 1, 2, 1, 1, 4. So we're taking the coefficients, and that's our matrix form. And this is our, we're going to augment that. And when we do that, we go here. So this is our augmented version. So it's a very similar arrangement in terms of what we're trying to do and solve these points. We don't want to lose sight of that, because often when you do matrices, that's exactly what happens. The meta idea evaporates because you get caught up in all this other stuff that's going on. But because this looks very foreign, so the way that I've got this is I've effectively got the y columns, the x columns, and the constant columns. And so what I now do is follow the procedures for matrices to solve this system. And I want to do a 3-by tonight and talk a little bit about row down column multiplication. So what we do as a process, and it doesn't matter if you did Calculus 1 and you can't remember any of this. This is part of the reason I'm revisiting this, because some of you haven't done Calc 1, is I want to target that guy, and I want that guy to be a 0. So if we've got row 1 and row 2, literally across the rows there, what I would do is I'd take row 2 and I'd subtract from row 2 row 1. So over here I'm going to have row 2. This is my rule that I'm making up out of my head with the goal of making this a 0. So row 2 is going to become row 2 subtract row 1. So it's a simple rule. So if I run down row 2 and put all the numbers and the minus signs and the equals, and then run down the corresponding row 1, I'll get that. Now, dealing with matrices is very, very time consuming, but there's great power in the mathematical world. And my job is to entice you guys to really love them. And I've got about 6 or 8 weeks to do that. And in the context of your school careers, where you're not using them, it's a bit of a challenge for me to get you enthused. It's a lot easier for me to get you enthused about the 6 points and know-how sessions and those techniques that apply to your current studies. But to get you, this is how you become a mathematical scientist. Linear algebra is the answer. Okay? So if there's a gap, it's not going to be DEs at some extraordinary level. It's not even going to be analysis, which is about proofs. It's not even going to be Lebesgue's or line, you know, all of these path integrations, all of this kind of stuff. It's going to be linear algebra. And all of the big data noise that you hear around, the way that that's approached is through the lens of linear algebra. So I would like, I think, has anybody actually done the linear algebra subject with when it ran? So you guys didn't do it? Because there's actually a subject called linear algebra that you can do for these degrees that you guys have been engaged with, these postgrads. Alright, so we've ticked a box here, we've got the 0. So row 2 has become 0 in that first placeholder. It's become 2 there and it's become 2 there. So if I rewrite this, I didn't do anything to row 1, so it doesn't change. Row 2 now looks like this. And so what I can do here, this is often called a back substitution point. I often call it just a rebuild. So I just take the elements as I see them. So what I've got there is 2x is equal to 2, reading that array. So that's going backwards. So the first step we did was the augmentation, which pulled the coefficients out. Knowing that we've got coefficients only here now, I can then pull this across. And you'll notice what happens when you solve this. You can get to that same solution, the way that we did simultaneous equations. Now you can do simultaneous equations at high school, not by doing the equals, but by substituting one of the values back into the other equation. And that's okay, you can do that, that's not an error at all. But this matrix idea here has another part to it, and that is that if we continue with our matrix operations, we can then produce a matrix which we can read the values straight off. And when you've got computers involved, that's a wonderful thing. So we're going to target this guy here, and I just want it to be 1. So I'm going to take row 2, and row 2 is going to become row 2 divided by the number 2. So I'm not changing anything else, and I don't have to do expansive. 0 divided by 2 is still 0. 2 divided by 2 is 1. 2 divided by 2 is 1. Now you can see that x equals 1. If I did a rebuild here, a back substitution here, x equals 1. So I've done that. The next thing I'm going to do is make that one a 0. So these patterns that I'm picking, there's a procedure for that. There's actually a bunch of rules that help you pick why did you start there, and then why did you go to that one and not that one. Okay, so when you do those particular operations for this echelon reduction, and there's different levels of echelon reduction, I'm heading for the highest level, so that we can just read off the values. So I want that minus 1 to be a 0. So what I'm going to do is I'm going to say row 1 is going to be row 1, so add row 2. Now because I've done this in a particular order, when I add 0 to this 1, it won't change it. So I'll just put them all like that. And then our row 2 is 0, 1, 1. And all that. So the kids at uni hate this because of the discipline it takes to just wade your way through all of this. So 1 plus 0, oh, that's still 1, so I haven't changed that, tick. Minus 1, oh, I got it, I got a 0, so tick. And then 2 plus 1 is 3, which is neither here nor there. So we've got 1, 0, 3, 0, 1, 1. So what we're able to do is read these values straight off. So therefore y is equal to 3 and x is equal to 1. If you do a mental rebuild, this is y equals 3 and this is x equals 1 if you rebuild the coefficients. So the power of the system of equations is really helpful, and often it gets messy and laborious, and it's quite terrible. So it's possible if we take x equals 1 and put it in any one of these equations, we'll get the same one. Okay, we'll get the same result. Okay, so in the national curriculum they do actually do matrices, and I've put some companions up on the Maths Study Centre website, so you can scrub back through the video. But here we go again. And when you go to resources, you can scrub back through the video to see all this. Now, no, that's not what I wanted. Modelling for science. Sorry, one more. Must be modelling 2. That's an older subject now. Ah, there they are. The maths companions and the stats companions. So these two guys are based on the national curriculum. So if I open that one up, it's got the high school version of solving equation systems of equations. So if you're really interested in this, it's got some directly relevant resources to the current curriculum, but it's got the additional look at matrices. So you might find that helpful, and you can download that PDF. That's a kind of cursory thing. And the other one, oh, Statistics Companion, I've still got that open. Alright, so there's a Statistics Companion. This is the high school way of looking at statistics, but it's done not quite as aggressively as it's done in, say, the Cambridge books. Or what's the other one that's popular? I can't think of it off the top of my head. So if you want to have a look at a couple of alternative ways of looking at you know, your curriculum, these are very good resources for you to do. Okay, so that's enough of all of that. One more. Great. Okay, so one of the things that comes up is that we often have matrix multiplication. Now, in matrix multiplication, the rule for matrix multiplication is they can be square or they can be circular. It doesn't really matter. They can't be vertical bars because vertical bars means a special thing. So if I take A, B, C, D, and then I have another matrix, usually they have to be square. So E, F, G, H is one example, comma, another example, and you'll see the matrix multiplication in those resources if you open them up. But E and F, I'm going to do it that way now. So what you can do is you can multiply your matrices, the column matrix. So how do we do multiplication? Now this is referred to as matrix algebra, this top row here, and basically it is usually all in bold, and all of the rules around matrices are explained through the lens of that matrix algebra. The actual doing is done with these guys. So when you do a multiplication, you do what's called a row down column. Okay, and you end up doing a sum of products. We've seen that before with the dot product. And yes, they're all related. And I'm going to try and show you something there tonight. So the way that we would do this is that we would do A, B, C, D, E, F. I'm going to repeat this a couple of times. And the row down column part is this row down this column. Okay? So what we would get is A times E, sum of products, plus B times F. And that would be our first placeholder. For the second part, we would go row down column. So we would have C times E plus D times F. And so that would be the sum of products for that in its entirety. Now when I do something like that and then make a quiz up about, oh well, are there certain sizes of matrix that you can't multiply? Yes. You know, you can't do this one times this one because there's only row down column. It's a mismatch, so that won't work. So when you get through all of that kind of thing, you do the nitty-gritty of the learning and you forget this meta idea. So one of the things that happens when you do matrix multiplication is something fascinating happens. And it's where we're headed after STUVAC. So that's why I'm doing it tonight, as a bit of a know-how. Because this is all revision, strictly speaking. So if I put a 2, 1 vector in, okay, as a column vector, and call that A, and because I'm not bolding it, I'll just put the thing underneath. And we did a little bit of revision. The vector A would look like this. It would be 2, 1. It's a column vector with 2, 1. Now, what I'd like to do is I'd like to do some mathematical magicry, and I would like to move it from being a 2, 1 to a 2, 1, 2. So in other words, I would like it to become transformed into the B vector. Now that is effectively a transformation. Now, I know you guys are very good at listening and being astute, and you're good students. You're much better than I deserve. But I also hit you with a lot of stuff, don't I? So here we go. So I don't often go to tell you guys about YouTube because you're probably fed up to the back teeth with YouTube, with all the people that get on there. Okay, but there is one thing that is worth us doing. 3 blue, 1 brown. So that 3 blue, 1 brown, there's a mathematician, that was him showing up there in the US, that's made this channel up, and I highly recommend it. I know people, this is for you, again, for staff, it's not for students, although there might be some of your better students who can cope with it. Because it's very easy to get distracted and lost, and I heap stuff on you, which is why I was saying you're such good students, because I know you drink it in, but you've got to use some wisdom too, okay? Because you can spend hours and hours. But there's 16 episodes in the essence of linear algebra. I'm not going to, it's not a task, there's nothing for you to do, there's no surprises in terms of why I'm presenting it. It's just to give you another resource. But I'm just going to turn on the recorder and the sound for this channel, and let's get to some rubbish. I'm going to do linear transformation.
When I finished Year 12, I got an ATAR of 99.
Good on you, mate. Just wait for the ad to disappear because I haven't paid for this one. So I'm going to scrub through this. A bit annoying because it's exactly where we're at on the white sheet. Can you hear that? Can you hear the sound coming through the...
Hey everyone! If I had to choose just one topic that makes all of the others in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one.
I think that's what I just said.
The idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of 2 dimensions, and how they relate to the idea of matrix vector multiplication. In particular, I want to show you a way to think about matrix vector multiplication that doesn't rely on memorization. To start, let's just parse this term, linear transformation. Transformation is essentially a fancy word for function. It's something that takes in inputs and spits out an output for each one. Specifically, in the context of linear algebra, we like to think about transformations that take in some vector and spit out another vector. So why use the word transformation instead of function if they mean the same thing? Well, it's to be suggestive of a certain way to visualize this input-output relation. You see, a great way to understand functions of vectors is to use movement. If a transformation takes some input vector to some output vector, we imagine that input vector moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid.
I'm going to drop
you
this
give
off
the computer
now, sorry.
So that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands. Watch the transformation itself.
I'm just trying to tease you a little bit.
Write the vector with more general coordinates, x and y, and it will land on x times the vector where I hat lands, 1, negative 2, plus y times the vector where j hat lands, 3, 0. Carrying out that
I'm
sum...
just going to pause it there now. So what I'll do now is our version, okay, our version, and our version is the one that's probably more relevant. So how do we get this to happen? That 3 blue 1 brown video goes into it in a bit more detail. How do we get this to do? Well, it turns out that all we do is a matrix multiplication. So some of the very sophisticated space-time problems that come up in mechanics, physics and other areas, finance and the like, use all of our calculus techniques couched inside these matrices, and that's where we're headed after the STUVAC. We're going to have a look at systems of equations that have got DEs in them, and I'll walk you through it. I'll hold your hands. I'm not going to ambush you and make you feel that it's not right, but we'll manage it in a way that hopefully you come away going, gee, I really would like to do some more on that. Okay, because these courses that you've been doing, they're the answers. If you've got an inquiring, curious mind about how the horsepower works in terms of how does the rocket get built, how does the bridge get built, how does the economics work, all of those things, steepest descent. We don't do that in this subject. We did it last in Calculus 2, didn't we? We did steepest descent when we did Lagrangian multipliers and all the rest of it. So how do we do it here? How do we do it with this one? Okay, so if I have let's try and do it, let's work it backwards. Let's try and cheat a little bit. Don't like using that word because we're not really cheaters. But let's take our first matrix and apply some transformation to it to get our second column matrix. And when I say column matrix, we can call it a vector. So we're going to take our initial one, which was 2, 1, and we want it to become 1, 2. So just like the little video talked about functions in and out, we've got a transformation vector, a transformation matrix. I'm going to take that off the bottom of that. Just take that bit off. So the transformation matrix, and that transformation matrix is going to do what? It's going to do row down column, row down column. So let's think about what we can put in as placeholders in these particular locations so that when we do a row down column we get these results. So the sum of products means that we'll get row down column, so we get something times 2, this something times 1, this something times 1, and we sum them because it's the sum of products. I might just take that out. Okay, so we want that guy there to be a 1, so let's think about what can go in the brackets. What are the numbers that can go in the brackets that give us the result of 1? Because this is the sum of products. So we've got something times 2 plus something times 1. What's something, and we've got to be a bit creative, not too creative. Well, I want the 1 term, don't I? I don't want to modify the 1 term, so what's something I can multiply 1 by not to change it? My favourite number? 1. So if I multiply 1 by 1, in other words, if I multiply this by 1, row down column, I will get 1. Goal achieved. What can I put in the bracket for the 2 so that it doesn't modify this value 1? What can I add to 1 that it won't change it?
0.
Ta-da! 0. So if I do a row down column on this top group here, this is the line that I will get, the sum of products line. Alright, let's see if we can do it again for this one. The result that we want this time is 2. So we're going to have to do row. So we're going to go row down column. So we'll have something times 2 plus something times 1. What can we think the somethings might be? So what can we multiply 2 by so that it doesn't change?
So I multiply 2 by 1 and then multiply 1 by 0.
Awesome. So you can see there's a pattern. Now, we don't normally develop our understanding of this process this way. This is a bit of a Jasonism. Okay? So just be warned about that. But the idea is that, look at this thing. This is a transformation matrix that rotates this or reflects this about the line y equals x. Okay? Now look at the power of information in that. That's amazing. Okay? So in that particular example, what we have is a transformation matrix. Now there are many transformation matrices that do all kinds of things. Reflect vectors in the y-axis. Reflect them in the x-axis. Rotate them. Like that. There are many different matrices that are transformation matrices, so that when you apply them to a vector, it does some output thing to that vector. So the concept is not hard, but what I find is that most students, like the video said, get caught up doing all the bits and pieces and lose sight of the big picture. So in this case, this is a very simple demonstration of a transformation matrix in play. Now there's another special type of transformation matrix. Who can tell me what that is? Because you guys that did do calculus 1, I'm looking at you. Who can tell me what it is? Okay, so if we've got a vector, and if we think about all the possible places that the vector could go, it could go in reverse down this way negatively, it could increase and be stretched out longer, but this special type of transformation isn't going to knock it off this span. It's going to remain on the span of the vector. So whatever this vector is, if we apply a transformation matrix to it, okay, and let's give it a value 1 1, all that's going to happen when we do our row down column is that we're going to get maybe we'll get negative 1 1, maybe we'll get it flipped in reverse, so it goes negative 1, but it still would be on the span. Okay, so I've chosen 1 1 there. So if I did it that way, it would be negative 1. So what would that transformation matrix have to be in order to give us the reversal? Okay, what would the transformation have to be? I might just change colours if that's okay. So this is very, very important, and this is a great, it should, how can I phrase this? A great opportunity, blessing, look, gift horse in the mouth, whatever you want to call it, in coming to uni and doing this, these subjects the way you have. Okay, so this transformation matrix might stretch it. It might take the 1 1 and keep it on the span and move it up to 3 3, and so it would come up to this point. So that would be 3 3. What would be the transformation matrix that would do that? So that's a stretch. Okay, and I'll do one more if that's okay. What would it be if we did a transformation matrix on our vector, and we'll call that V all the way down, which is 1 1, and this time we shrunk it, so there's some transformation matrix we can do a row multiply by, and we get a half half. Okay, so this is a shrinking, so the vector becomes half half. So this bit tonight that I've done with you, I just don't want you to forget it, okay? Because after the semester, when we start looking at systems of DEs, all the stuff and all the noise that's there, what are we doing it for? This is the reason we're doing it. We're doing transformations, okay? The transformations are a particular skill, and so these are all examples of a particular type of process and procedure that you went through if you did do, and they're called eigenvalues and eigenvectors. Now it turns out, if you recall, that's what that whole process was about: stretching, shrinking, but not rotating or reflecting, but just doing this kind of thing, keeping it on the span, that potential possible location. Now, do you remember that at all? Anyone that did it? Maybe it wasn't clear, but this is what you're doing. Now it turns out that the relationship, as in most things mathematical, is that there's some matrix, so I want to be careful how I do this. There's some matrix, that's very unconventional what I just did, but I'm doing it anyway, that you can apply to your vector that is the same as some scalar or a number. A scalar is just a number that gives you the same result. In other words, you don't only need the transformation vector, you can just have, and this thing here is called your eigenvalue. So they're an equivalent, and that's your equivalent using the transformation matrix. So this is the hardest thing that you come to terms with in matrices. I know there was a lot of stuff in matrices, but this is the hard one. Okay, this is the one. Processing this and getting this out relatively easily is not straightforward. So it's an equivalence that allows you to think about if I could just find the number, then I could just multiply the vector by the number to get the shrink, reverse, or stretch that I was looking for. Okay, if I could just get the number. Otherwise, I would have to do the multiplication. Now, it turns out they teach you to do that multiplication in any case. But when you hear eigenvectors and eigenvalues in the future, whenever it comes up in topical conversation in your professional reading or watching 3 Blue or 1 Brown, that there, folks, that's it. In a nutshell, what you're seeing there is what it's all about. Okay? It's not complicated. It's just that all the noise that you go through to get to this point is quite a lot, and so can be a distractor. So I really encourage you as we go forward, and I'll meter this stuff out so that we don't, get over the top with our efforts and energies. All right. So, has anybody got any thoughts about that? Have any memories of that from previous work you've done? Want to make a comment or? No.
I do remember doing some of this with like my first year maths. It's
But that was a
slowly
long time
coming
ago.
back.
Yeah.
Yeah.
Yeah. I mean,
well, my first year maths was back in the mid 1980s, so I kind of vaguely remember it. In fact, I've got my very old textbook, which I'll pull out and look at.
yeah. And the idea is that it's a whole recycling of ourselves when we revisit things. I think I let you know about some open book exam I did, and I couldn't. The book for that subject, I couldn't read it. It was like they may as well have been hitting me in the head. I had to get other texts and get other sources to understand it, and it wasn't until about 5 years later that I was able to pick that book up and read it. So that was just my example. I've heard that with other people. Some people can just pick a book up and read it and know it, so lucky, good for them. But for this part, I feel as though this is worth playtime. It's worth having a look at, thinking about more. Now I know you've got your schoolwork, and I guess that's preoccupying you, but in your career, in your formative career as you move forward, if you want to know more about the way the world works and how it all snaps together, linear algebra is the lens that you want to be applying to that. The calculus is good, but it needs partners. The calculus needs friends and it needs helpers, and there's no better helper than linear algebra, and I hope to show you that this semester in a careful and metered way. So what I'm going to do is I'm going to set up how to do the eigenvector eigenvalue business, but I'm not actually going to walk you through it tonight. I might leave that till next week, okay? Because I have done a lot, haven't I? It kind of your head starts to bulge a little bit, and in the context of everything else, that's a lot to take in. So I'll just set it up a little bit, and we can stop and move on from that.